Hello everyone and welcome. Today we're going to solve a fascinating problem from quantum mechanics, finding the angle between an electron's spin angular momentum vector and the z-axis. Understanding this concept is crucial for grasping how particles behave at the quantum level. First, let's visualize this. Imagine a three-dimensional coordinate system with x, y, and z axes. The z-axis is our reference direction. We have an electron, and its spin angular momentum can be represented as a vector, which we'll call s. Its component along the z-axis is sz. Our goal is to find the angle theta this spin vector s makes with the positive z-axis. Now, let's identify our key variables. We're interested in sz, the z component of the electron's spin angular momentum, and y prime, the magnitude of its total spin angular momentum. Both are expressed in terms of h bar, the reduced Planck constant. For this problem, we are given that sz equals 1/2 h bar, and y prime equals the square root of 0.75 h bar. The core principle we're using here relates a vector's component along an axis to its magnitude and the angle it makes with that axis. Specifically, the z component of the spin vector sz is equal to the magnitude of the spin vector y prime, multiplied by the cosine of the angle theta between the vector and the z-axis. So our relevant equation is sz equals y prime cos theta. Now let's substitute our known values into this equation to solve for theta. We have 1/2 h bar equals square root of 0.75 h bar times cos theta. Notice that h bar appears on both sides, so we can cancel it out, simplifying to 1/2 equals square root of 0.75 times cos theta. Since square root of 0.75 is the same as square root of 3/4, or square root of 3/2, our equation becomes 1/2 equals square root of 3 times cos theta. To find cos theta, we divide 1/2 by square root of 3/2, which gives us cos theta equals 1 over square root of 3. Finally, to find theta, we take the inverse cosine, or arc cos, of 1 over square root of 3. Using a calculator, theta is approximately 54.74 degrees, so the electron's spin angular momentum vector makes an angle of about 54.74 degrees back into our equation. Cos of 54.74 degrees is approximately 0.577, which is 1 over square root of 3. Multiplying s, which is square root of 3/2 h bar, by 1 over square root of 3 indeed yields 1/2 h bar, matching our given sz. This consistency confirms our solution. Our finding of approximately 54.74 degrees for the angle highlights a key quantum mechanical property. Even though the z component of an electron's spin is precisely quantized, the spin vector itself isn't perfectly aligned with the z-axis. This intrinsic tilt is why the total spin magnitude, square root of 0.75 h bar, is slightly larger than its maximum z component. This concept is vital for understanding phenomena like electron spin resonance, and even magnetic resonance imaging in medicine. In summary, we used a fundamental trigonometric relationship to determine the electron spin angle, demonstrating how classical vector concepts extend into the quantum realm. This problem emphasizes the distinction between a vector's total magnitude and its quantized components, a core idea in quantum physics. Thank you for joining this session. I hope this explanation was clear and helpful. If you found this video useful, please give it a thumbs up, subscribe to the channel for more physics and math problems, and share it with your friends and classmates. Feel free to leave any questions or comments below. And if you have a specific physics or mathematics problem that you'd like to see solved in a future video, consider supporting the channel through a donation. Each month, we'll select a few donor-requested problems to solve and explain in detail.